everyone. For those of you who I don't know, I'm Zoe Almeida. I'm a new Senior Research Associate at the Cornell Biological Field Station, and I work with the Warm Water Fisheries unit there. And today I'm going to be talking about some of our data on walleye that we have due to some of our long-term collections, and looking at what factors are most likely to affect walleye condition, growth, and length. Before I begin, I want to thank Dr. Pat Sullivan for help with the analyses, and this is based off of long-term data, which requires generations of crews as well as generations of funding, and without that, none of these cool questions we can ask would be possible. And in particular, I would like to very much thank Dr. John Forney. So for those of you who were in John Farrell's plenary, you'll have heard that he recently passed. And if it wasn't for him starting the field station and starting this long-term collection program, none of this would be possible, and he's made an outsized impact on New York fisheries as well as just the whole field of fisheries in general. So I think most of you are aware that environmental variability makes managing populations pretty challenging. You have different systems that have different temperatures, they've got different prey communities at different abundances. Your focal species, it exists in different densities in those habitats, and then to make this even more challenging, all those things change over time. So how it was in the 90s is not how it is anymore. And one of the tools that agencies use a lot is manipulations of density. So either through additions with stocking or deletions, increasing stocking or harvest regulations to decrease populations. And when we're trying to understand the effect of density on these populations, it can be a little bit complicated by all those other environmental variables, since those changes in density might obscure the effects of those other environmental factors on the populations themselves. And so, in general with this, I was hoping to use our long-term data set to explore some questions about what are the consequences of densities, changes in densities, and can we actually distinguish those from other environmental effects? Our study system is Oneida Lake Walleye, and that looks very tiny on there, but Oneida Lake is a very large lake. It is not a great lake. It is a large, shallow mesotrophic. It's the largest lake fully contained within the state of New York. And as with many freshwater systems, it's been experiencing a variety of environmental changes over time, including recent rapid warming, as well as a lot of invasive species. Oneida Lake walleye are a valuable and well-loved sport fishery, and due to, again, the works of from Dr. John Forney, it's been well studied in the lake since the late 50s. And recently, so for those of you who don't know the history, Oneida Lake walleye had a bag limit of 3 fish, which was different than everywhere else in the state. That was recently increased to the state's level of 5 fish per person per day. And so we were kind of interested in whether this density decrease would actually increase the body condition, growth, and size for walleye in the lake. But again, we weren't sure if we could actually tease apart the effects of the additional effects of changing prey and temperature as well. All right, so objectives here were to determine which combination of density-dependent and independent variables best explain condition, growth, and size, and then quantify if and how those relationships changed over time. I'm going to say right now this is still a preliminary analysis, and so please, please, please come talk to me if you have other suggestions or thoughts for what these results end up looking like. But yeah, that's maybe ahead of myself, but please talk to me. All right, so we tend to expect that with temperature, so with growth, we assume that with warmer water, we're going to see higher growth up until a point, at which time it might become detrimental. So we expect a curve kind of like this. And we often expect condition and size to actually follow similar trends because we think that they're kind of affected by similar mechanisms. With prey, we expect more of this relationship where more prey does equal higher growth up until a point. It doesn't decrease, but it just sort of levels off as the system gets saturated. And then with density, we expect the sort of inverse of that relationship. With greater density, we have lower growth up until a point, again, saturation of that response. And then over time, this is a simplifying assumption, but we assume that those relationships don't change over time. So the way that temperature affects growth, we assume that that is responding in the same way as in the 90s as it does now. All right, so for this, we used relative weight as our index of condition. For growth, this was an average change in cohort length, and for size, we used length of walleye at age 6. For relative weight, we did this as an annual mean relative weight of age 1+ individuals that were collected in the fall from 1986 to 2022. For growth, this was, we used an annual change in, we used mean lengths at age from fall surveys, and then we got the growth at age as a mean difference in those lengths at age, and then we used an age length residual since growth can be affected by length as well as age of individuals. And then we focused specifically on early or young adults, so ages, average the growth of ages 4 to 6. For size, we looked specifically at age 6, length at age. For our predictor variables in this, we used annual values for condition and growth, and then for our size, we used cumulative values across those 6 years of life. And then for our density-dependent variables, one of those was just our estimate of the adult population, so age 4+. We didn't actually include that in the length analysis. I'm open to discussion whether that was a wise choice or not, but we thought cumulative density experienced over 6 years didn't quite make sense. For density-independent variables, we have a prey biomass, prey index, which is basically a summed biomass of 4 different common prey items for prey fishes for walleye. And then another density-dependent factor was actually per capita prey abundance. And then temperature. So we used cumulative degree days during the growing season for adults from mid-October. The model we used for this was a generalized additive model, and the reason we did that is that we didn't have to assume the shape of the relationships. We could let sort of the data tell us the best shape. And so for each of our response variables, we had various different thin plate regression splines. So for population, prey, temperature, and year. And we used shrinking with that to extra penalize extra curviness. And then for each of these models, we used an autoregressive model of order 1 to account for temporal autocorrelation. Now, we used model selection of these different GAMs, so using various combinations of these individual smooths. We also, whenever we use per capita prey, just to note, we did not also use population or prey in those models since they went into forming that predictor variable. And so we had these individual smooths, and then we also looked at models that looked at sort of interactions between these, so tensor product smooths between 2 of the variables. And then for all of these, we accounted for temporal autocorrelation. Just a note, so we excluded any models that had pairwise concurvity of smooths that was greater than 0.8, so that's a lot like covariance, so like if the smooths between prey and temperature were too similar, we wouldn't be able to distinguish them in the model, so we excluded those models. All right, so for our results, for relative weight, these were our best models, and our best models included indicators of density, prey, and year. As a reminder of our expectation, we thought that there'd be higher per capita prey correlating with higher condition, and that this wouldn't change over time. So our results I'm going to put on this color contour plot. So just to orient you, the x-axis is year, the y-axis is per capita prey, and then on that plot I'm going to have our response variable, which is going to be different colors, with warmer colors indicating higher condition and cooler colors indicating lower condition values. And we saw that we actually did see that higher per capita prey does correlate with higher relative weight. If you go up that y-axis, you see warmer colors in general. One thing that we did see also was that there was kind of a shift in this relationship in the early 2000s, which was kind of interesting. So if I were to just doodle this, because this is kind of easier to see than color contour plots, before the 2000s, we see this shape of the relationship, which is kind of what we would predict. But after, we see this change in that relationship, where there's higher per capita prey needed for that greater positive effect on condition, and in general, it's a weaker effect of per capita prey on condition. All right, for growth, our best model included population in year, and again, as a reminder, our expectation, we have this lower growth with greater density, and that this doesn't change over time. This was our results with population again. Population on the y-axis, year on the x-axis, the colors indicating our response, which is in this case growth. One thing that stood out immediately was just that more recently we've had lower growth. So after about the year 2000, we have lower growth. But then also after the year 2000, our shape of our relationship seems to change again. So back to my doodles, because that's a little bit easier to understand. Before 2000, we had this kind of, I was getting this confused, concurve relationship. After 2000, we have this more convex relationship. Anyway, they are inverted. I don't get it. Please come talk to me. See if you can explain this to me better than I can understand. And then for age 6 length, our best model included prey and temperature. This was our expectation for that. And then with size, we do see that they are, in fact, larger with more temperature. So to orient you, x-axis here is our degree days, our temperature, and then on the y-axis is prey biomass. So as it gets warmer, we are seeing larger size 6 individuals, but we're also seeing a slight effect where it's actually, they might get smaller with more cumulative prey. So if you go up that y-axis, the trend decreases. So that was a bit confusing. All right, as I mentioned, this is preliminary. Please come talk to me if you can understand this better than me or have other suggestions. But to quote Dr. John Forney for this, walleye are pretty unpredictable. So I have seen that throughout my whole career, so this seemed appropriate. So we see that density isn't actually in the best models for all of our responses. Which is interesting because, like I mentioned early on, we often assume that size is affected by similar mechanisms, or that what changes in condition and growth are going to be reflected in the sizes that we see. However, our best models differ. We saw density being important for condition and growth, not always in expected ways. Again, can someone tell me what's going on with growth there? I don't know. And then we also see changes in that over time, which we were not expecting. However, if you're interested in changing the density in a system, it might benefit condition. I'll say that. It looks like it might benefit condition. I'm not sure if it will affect growth, or how it will affect growth, or what other factors might be affecting that. So come to me later, maybe I'll have it figured out by then. And then this also raised the question of what happened in the early 2000s. So over time in Oneida, we had some invasive species. We got zebra mussels and quagga mussels coming in around that period, changing water clarity. We also saw over this time decreasing winter severity, which we actually had our first year of 0 ice duration right in that early 2000 period. So maybe that. All right, and then for size, interestingly, we saw that temperature was important for size, but not for condition and growth. So as a caveat, density might still affect size, and temperature might still affect condition and growth, especially at different ages that we looked at. They just weren't the most important factors in these models. That effect on size, it could be that there's selection going on, where at lower temperatures there's more even distribution of mortality across sizes, but at warmer temperatures it's all the smaller ones, and maybe that's happening at an earlier stage than age 6 because we're just looking at age 6, all those things. Anyway, our next steps are to examine if the effects of water clarity and ice cover to see if those are maybe causing some of those changes that we're seeing in early 2000s. Try to figure out what's going on with growth. Again, please come talk to me. And then I kind of am curious about the temperature size rule and what role that might be playing up here. So with that, does anyone have questions, comments, or suggestions if I have any time left? I know I want to pass it through. Okay.
Questions?